Hello, everyone. And today we are going to discuss strategy which we use for testing series. Basically, that's a big review of what all possible tests we can use to test a series and like different kinds of series about which we already know that they are convergent or divergent. So guys, on the left side, my whiteboard, let's say pinboard, I have like 6 different series. On my right side, I have all tests we learned so far. We started with divergence test. Remember, a series is divergent and the limit, if limit of the term does not go to zero. Term must go to zero. If this does not happen, the series is going to be divergent. Then we had 3 special series. We had P series, G series, and I would say separately H series, which is actually part of P series, but because we are going to use actually name of harmonic series separately, so I separated them into kind of different line. So for P series, we know that what? The test is P supposed to be greater than 1, the power of that n, right? For G series, R supposed to be less than 1, right? For harmonic series, we have like harmonic is divergent and alternating is convergent, alternating harmonic, right? For divergence test, limit of an is equal to 0, right? If it's not equal to 0, it's divergent. Comparison tests. We had 2 comparison tests. One was direct comparison, and one was limit comparison. Both comparison tests are using some known series, and usually it's going to be one of P, G, or H series to compare a known series to it and make a conclusion about convergence or divergence, right? Next test we learned was alternating series test. Usually works when you have sign alternation, like plus minus, plus minus, plus minus. And alternating tests can make only conclusion that the series is convergent. It cannot make a conclusion that the series is divergent. If test is not working, really can't. We just need a different test to test the series. Ratio and truth tests are comparing our series with geometric series. And if we think that series looks like geometric, we can find the ratio. And if ratio is, in this case, limit less than 1, then it's convergent, greater than and divergent, and equals to 1, inconclusive. Greater than 1 equals to 1. So this is good, and these 2 in parentheses are bad, right? We also learned integral test, and was actually the very first test we used to deal with P series and show that harmonic series is divergent, right? Integral test. Usually, if we see that the expression under the sigma can be integrated. Remember that infinite series and improper integrals, which means infinite integrals, are going to do the same. Either they convergent or divergent together. We also have a special theorem about absolute convergence. Remember, if you have a series where you don't see alternation of signs or terms are just changing a little bit sporadically, then you can use absolute convergence theorem. Means that you can take minus out of your series, investigate absolute convergence. If the series is convergent absolutely, then it converges, right? And mostly the tests above, like comparison tests, for example, are working with positively termed series. Also, integral test is working with positively termed series. Ratio and truth tests are testing for absolute convergence too. They're not testing just like convergence. Sorry. And like there are 5 different series. Guys, maybe you kind of want to spend like a couple of minutes and think which test can be used against each series before I tell you. So you can stop the video, try to think like which series belongs to which test, and then kind of start the video and see how I will do this. Okay, so 1, 2, 3, pause your video, and I'm going to count 1, 2, 3, and then going to start explaining. Okay. So 1, 2, 3 again, and you can start it. And let's check which series belongs to each test, right? And guys, I'm going to start with series number 1. And what I see, guys, n divided over ln of n. I know that n is growing faster than ln of n, so probably this expression actually goes to infinity. And the first test, like, which comes to my mind is divergence test, because if term does not go to zero, definitely the series is divergent. So I'm going to connect actually my first problem with divergence test. My second problem looks like a rational expression. Remember, guys, for rational expressions, the best test, unless it's alternating, it's a comparison test. And you can use direct comparison or limit comparison. In this case, I would suggest you to do limit comparison, because looks like we are modifying with number both numerator and denominator, and these modifications are working against each other. Normally we compare it to p series, right? But I'm going to make it probably a second arrow to show that comparison tests and p series, right? The next problem looks like we can integrate it, right? Looks like 1 over n is actually derivative of ln. So we can kind of introduce a new variable u, which is ln of x, and try to integrate it and see what is going to happen. I'm going to connect it to integral test. For some series, you can use different tests to prove that it's convergent or divergent. So, well, I would use integral test, but maybe comparison test is going to work also. For number 4, guys, looks like we have rational expression and -1 alternating. So I would try alternating series test. And if it does not work, maybe then my kind of next step is going to be divergence test. My series number 5 has n squared. N squared means that it's n multiplied by n. Maybe I want to get rid of one of these n's and use root test. So I'm going to bring it over here, and more specifically, I'm going to bring it to the root test. But again, root test and ratio test are full tests, and you can use ratio test too. Just gonna be longer. And the last problem, factorial, 2 to the power of n. Well, we don't know what is nth root of factorial, so maybe we should just use ratio test. So I'm going to bring again to here, but I'm going to go to ratio test. So let's say we did not use G series and H series, which is just good to know that H series is divergent and alternating is convergent, right? G series is actually using in ratio and root tests, right? We are doing comparison with, and sometimes we use G series for comparison tests too. So it's just like it did not happen over here, but can happen like when you solve a different problem. Absolute convergence theorem. Also, there is no problem which requires like use of absolute convergence. But we remember that actually ratio and root tests are investigating on absolute convergence. So basically, after you use ratio test, you say that the series is convergent absolutely, and then it's convergent. So we kind of use it too. Now, what I'm going to do, guys, I'm just going to solve these problems, I guess. That's just going to be a good idea to show how we solve the problems, right? Let me use a different one. Okay, so I'm going to start with problem 1, and that's a series n over ln of n, and I'm planning to prove using divergence test. So I'm going to use divergence test and find the limit of term an as n approaches infinity. In my case, it's going to be the limit of n over ln of n approaches infinity. Guys, remember that we cannot differentiate natural numbers, but we can differentiate rational numbers, or we can differentiate real numbers actually. So I'm going to write down that it equals to a limit of x over ln of x. I know that this is just formality, but you can lose points because of this formality. And you see that we have infinity over infinity, probably use L'Hopital's rule, infinity over infinity. And let's find the derivative of x is equal to 1, right? And derivative of ln of x is 1 over x approaches infinity. And if we simplify this expression, we are going to have just x under this fraction flips over. And when x approaches infinity, it equals to infinity. So that term does not equal to zero. Even worse, it goes to infinity. So we are going to say that the series is divergent. I think I should use divergent small letter. By divergence test. Guys, if you ever wish to write down that something is convergent by divergence test, because the limit is equal to zero, just remember the words are the same, divergence and divergent. It's not going to be convergent and divergence. Okay? And let's move to our next problem. Problem 2 is going to be sigma n square plus 1 over n cube plus 1, and goes from 1 to infinity. And here I'm going to use a limit comparison test. So comparison series is going to be what? Series of Bn, and you can simplify numerator and denominator, keeping the greatest power. And you see n square over n cube, which is going to be equal just 1 over n. Guys, that's where we have harmonic. You don't need to prove that harmonic is divergent. Everyone knows this. Harmonic divergent. So now I'm going to build a limit. Limit between an and bn, and goes to infinity. I don't need any absolute value here because everything is positive, and limit comparison test works. It's positively turned series, right? And I'm going to write down limit n square plus 1 n cube plus 1, and goes to infinity divided over. Remember, guys, you found simplified version, but when you write down your limit, use this one. Use non-simplified version of your term. It's going to make your limit easier. So limit, I combine terms with same power together. Squares are combined into one fraction, and cubes are combined to another fraction. Now, guys, here I divide by n square, here I divide by n cube. And my limit is going to be 1 plus 1 over n square over 1. And here 1 over 1 plus 1 over n cube. And we know that when n goes to infinity, this will go to 0, this will go to 0, whole thing. And we are going to have limit equals to 1. For us, it's important that it's not equal to 0 and not equal to infinity. So actually these two series, our p series, which is divergent, and our series in the question, are kind of parallel to each other, or actually equal to each other at infinity, means that it's going to be divergent too. You can write down a n is divergent too. And again, start writing down divergent. Divergent 2. When you write down divergent 2, it's supposed to match what you say here. It's supposed to match this divergent, because I see students writing down in tests. The series is convergent and then it's divergent too. Or the series is divergent, it's convergent too. Well, you know that this divergent and this divergent must match each other because they are supposed to be either divergent or convergent both. Okay, good. We are moving to question 3. Question 3, a little review of integrals. So guys, I'm using integral test here, but maybe you can also use comparison test. Just like to show how everything is working, I'm going to use integral test. I'm going to find the integral from 2 to infinity of 1 over x square root ln of x dx. Well, doing substitution, I'm going to get d ln of x, right? If I differentiate ln of x, I'm going to get 1 over x square root of ln of x. Now I can kind of use du over u, which is going to, or not square root of u, which is going to give me what? 2 square roots of u, right? Why 2 square roots of u? When you differentiate square root, you're going to get the power 1 over 2, which cancels with this 2, and then 1 over 2 minus 1 is negative 1 over 2. We'll bring it into denominator. Let me go back to original variable and then put my limits. My original variable was again ln, so it's a square root of ln of x, right? My u was ln of x. My limits are from 2 to infinity. Actually, I'm not supposed to write down infinity. I'm supposed to write down t to limit t approaches infinity. Improper integral, right? So I have limit 2 square root of ln of t minus ln of 2 is just ln of 2, 2 square roots of ln of 2. When t goes to infinity, ln goes to infinity, and the square root of infinity is still infinity. So I'm going to get infinity. So my integral is divergent. I'm going to write down the integral is divergent. The series is divergent too. Guys, I don't write down anywhere here that I'm using integral test because I wrote it down over here. But if you did not write it down over here, you will need to mention integral test over here. Because otherwise I want to know like what you use. Okay? So that's problem number 3. And problem number 4, sigma negative 1 to the power of n over n squared plus 2 n from 1 to infinity. And I'm planning to use alternating series test, right? For alternating series test, I'll need first to find the limit of Bn as n approaches infinity, my condition number 1. You remember that Bn is everything besides minus 1. This is my Bn. So I'm going to find the limit n squared plus 2, n goes to infinity. I think here we can divide both numerator and denominator by n, and we are going to have something like this. Yeah, this one will go to 0, right? But 0 plus infinity is going to give me infinity, and 1 over infinity is going to give me 0. So term goes to 0. Checks. The second one is going to be a little bit more complicated. We'll need to check if the terms are decreasing, right? So bn plus 1 is less or equal than bn. Well, I think, guys, I'm going to use inequality here. I just not sure that should I use function. Remember, we can use function and then show that derivative is negative, then it's going to be decreasing, or you just can use direct inequality. I'm going to use direct inequality, see if it works. It works. If it doesn't work, I'm going to do the function. So the key point here is to not kind of write it down, like don't forget one somewhere. Most typical mistake people are doing. They forget one here or here, and then everything is not proving after that. So that's my inequality. I increased n by 1 unit everywhere in this term on the left. Now, guys, I'm going to cross multiply it. Why? Because everything is positive. So I have n plus 1. I think we had this series once in class, so it's not going to be that complicated. I'm going to open this parenthesis. N squared plus 2n plus 1 plus, you see, plus 2. I know we had it plus 1. I'm going to open this parenthesis. So n cubed plus 1 by n squared plus 2n by 2 and plus 2, 1 by 2. Less or equal, opening here is going to give me n cubed plus 2n squared plus 2n. I think I'm going to add up 1 and 2, so it's going to be 3n actually. 1 plus 2, 3n. Now I'm going to cancel some stuff. N cube cancels. 2n squared. 1 of n squared is going to cancel. 2n is going to cancel. 1n is going to stay. So I have 2 on this side. It's equal just n. Well, I do know that my n for the series starts with 1. So it's greater or equals than 1. So, of course, it's going to be greater or equals than 2. So everything checks. And we are going to say that the series is convergent by alternating series test. by alternating series test. If you write down AST, I'll understand it. But if you do exams for someone else, write down alternating series test. Okay, so we are done with number 4 and we have 5 and 6. Okay, let's move to number 5. Number 5, n over n plus 1 in square n from 1 to infinity. I'm going to use a root test. Use root test. So I'm going to find the limit. I'm going to extract nth root, absolute value of n goes to infinity again. You always can do ratio test when you do root test. It's just going to be slightly different or maybe a little bit bigger, longer. So if I extract nth root, I don't need absolute value here just because everything is positive. But when everything is not positive, you probably need. What is going to happen with my power? Well, you know that extraction of nth root is multiplication by 1 over n. So I'm going to have limit n over n plus 1 n squared to the power of 1 over n. So it means that square and n is going to cancel, and I'm going to have a limit n plus 1 to the power of n. Remember that power and power is just multiplication of powers. So guys, you see expression here. If you bring n to infinity, you're going to get somewhere here like 1 to infinity. You can use L'Hopital's rule here if you wish. Or what you also can do, recognize a special limit. Yeah, guys, what I'm going to do, I'm going to write down n plus 1 over n to the power of n. It's like I flipped over this fraction. I'm going to modify it. I'm going to divide by n. This by n and this by n to the power of n. Now, guys, this is a special limit, right? Limit as n approaches infinity, and this limit is equal to e. Just because this goes to 0 and this goes to infinity. Because over here it's upside down, this fraction, I'm going to get 1 over e here. Well, remember that e is approximately 2.7, so I have approximately 1 over 2.7. This is obviously less than 1. So we are going to say by root test the series is convergent absolutely. Okay, you see that it was obvious to use root test here because the power was n squared. Times, if it's not that obvious, don't use it. And my last series to investigate is 2 to the power of n over n plus 2 factorial. Well, I plan to use the ratio test. So I'll need to find the limit between an plus 1 next term and the previous term and check if this ratio is less than 1. Maybe it's not going to be that super easy, considering factorial, but let's do it. 2 to the power of n plus 1. Here n plus 2 and plus 1 more, it's n plus 3 factorial divided over 2 to the power of n plus 2 factorial goes to infinity. I don't need this absolute value here, everything is positive. I'm going to combine terms with factorial separately from terms with 2 n plus 1 over 2 to the power of n plus 2 factorial over n plus 3 factorial. And guys, if it's too fast for you, you can stop it and try to do it yourself. Simplify the fraction. I just don't know how fast your brain is working because I'm teaching basically nobody. And I cannot like adjust my pace. So the first fraction, you cancel 2 to the power of n, is just 1, 2 left, right? Here, guys, We remember that mm, factorial is product of all numbers from n plus 2 to 1. N plus 3 factorial is going to be product of all numbers from n plus 3 to 1, which is going to be n plus 3, n plus 2, and so on to 1. And this is actually n plus 2 factorial. And we are going to cancel it. And the leftover is going to be 2 over n plus 3. When n goes to infinity, kind of obvious that it will go to 0. Here 0 is not bad. 0 is actually very good. Means that it's always less than 1. And we are going to make a conclusion that the series is convergent. Absolutely. Here it's not going to make any change because series does not have any alternation of a sign. That's it. So we considered all examples, applied all different techniques. We did not use maybe G-series anywhere directly, but eventually you are going to see an example for comparison. For example, G-series or actually root and ratio test are both are actually about the G-series. Okay, that's all. And I'll see you next lecture.